Hey, sleepers. Tonight, we're delving into the quiet hum of the universe, the quantum void that powers everything. Imagine the deepest, darkest ocean trench, a place of immense pressure and stillness. Now, picture that even in that profound quiet, there is a subtle, invisible current, a silent tremor of energy that is never truly still. That is the realm we are visiting tonight, the secret engine of reality. So before you get comfortable, take a moment to like the video and subscribe. It helps more than you know. And for a bit of fun, share your location and what time it is where you are in the comments below. It's always fascinating to see where everyone is tuning in from. So close your eyes, take a deep breath, and get ready to drift off as we explore the gentle, persistent whisper of the quantum vacuum. Let's begin with a simple idea, one that feels intuitive and solid, the idea of nothing. If you were to take a box, a truly magnificent, futuristic box, and you were to pump out every single particle of matter, every atom, every wisp of gas, until it was as empty as human technology could possibly make it, you would be left with a vacuum. In classical physics, the physics of our everyday world, that would be the end of the story. You would have a box full of nothing, a perfect, silent, and empty void. But the universe, as it turns out, has a very different idea about what it means to be empty. In the strange and wonderful world of quantum mechanics, this perfect nothing doesn't exist. What we call a vacuum is actually just the lowest energy state that a system can possibly have. Think of it like the surface of a perfectly calm lake. From a distance, it looks completely flat, completely still. But if you were to zoom in, right down to the microscopic level, you would see that the surface is in constant motion. Tiny ripples and tremors constantly disturb the water, even on the calmest of days. The quantum vacuum is much like that lake. It is the baseline, the ground floor of reality, but it is far from empty. This ground state is known as the quantum vacuum. This isn't just a fanciful idea. It's a core concept of what is known as quantum field theory. This theory tells us that the entire universe is filled with invisible fields. There is an electron field, a photon field for light, and a field for every other fundamental particle that exists. These fields are not just mathematical curiosities. They are the fundamental fabric of reality itself. A particle, like an electron, is simply a localized vibration or excitation in its corresponding field, like a pluck on a guitar string. So, what happens in our empty box when all the particles, all the plucks on the strings, have been removed? The fields themselves remain. And these fields, even in their lowest energy state, are not static. They fizz and crackle with a baseline energy, a quantum restlessness. This is because of one of the most famous and perhaps most misunderstood principles in all of physics, the Heisenberg uncertainty principle. In simple terms, the uncertainty principle states that there are certain pairs of properties that you can never know with perfect accuracy at the same time. The more you know about one, the less you know about the other. One such pair is energy and time. You can never know the exact amount of energy in a system over an infinitesimally short period. Because of this inherent uncertainty, the energy in any given patch of space is constantly fluctuating. It can't just sit at a perfect zero. Imagine you're trying to balance a pencil perfectly on its tip. It's an impossible task. No matter how still you try to be, there will always be tiny, imperceptible tremors in your hand that cause the pencil to wobble and fall. The quantum vacuum is like that pencil, forever wobbling around its point of perfect balance, which is zero energy. These energy fluctuations are what make the vacuum a dynamic and lively place. And what does this fluctuating energy do? It creates particles. Out of seemingly nothing, pairs of particles and their corresponding antiparticles burst into existence. These are not the solid, stable particles that make up you and me. They are called virtual particles. They are born from borrowed energy, thanks to the uncertainty principle. They exist for the briefest of moments, a fleeting, ghostly existence, before they collide and annihilate each other, paying back the energy loan. Think of it like a very, very quick loan from a cosmic bank. The uncertainty principle allows the vacuum to borrow a tiny bit of energy, just enough to create, for example, an electron and its antimatter twin, a positron. But the loan has to be paid back almost instantly. So, the electron and positron find each other in the quantum foam and disappear in a tiny puff of energy, returning the universe to its ground state. This process is happening constantly, everywhere, in the space between the stars, in the room around you, and even within the atoms of your own body. The empty space of the universe is in reality a bubbling, frothing cauldron of these virtual particles, appearing and disappearing in a ceaseless silent dance. It's a bit like a cosmic soda, with bubbles of reality constantly fizzing to the surface and then popping back into nothingness. These fleeting particles and the energy they represent are not just a theoretical quirk. Their existence has been confirmed, albeit indirectly, through very real and measurable effects. One of the earliest and most famous confirmations is something called the Lamb shift. In the 1940s, a physicist named Willis Lamb was doing extremely precise measurements of the energy levels of hydrogen atoms. According to the existing theories of the time, two specific energy levels in the hydrogen atom should have had exactly the same energy. But Lamb's experiments showed that they were slightly different. There was a tiny, unexpected shift in the energy. The explanation for this shift turned out to be the quantum vacuum. The virtual particles popping in and out of existence around the hydrogen atom's single electron were ever so slightly nudging it, jostling it from its expected path. This constant, subtle interaction with the vacuum fluctuations was enough to alter the electron's energy level by a tiny, but measurable, amount. It was as if the electron was being gently buffeted by a quantum wind that no one had accounted for. Lamb's discovery provided the first solid experimental evidence that the vacuum was not empty, but was indeed a seething sea of activity. It was a profound moment, turning a strange theoretical prediction into a concrete feature of our reality. So this void, this supposed nothingness, is actually the foundation of everything. It's the stage upon which the entire drama of the universe unfolds. Every particle, every interaction, every force that we see is an excitation of the underlying quantum fields that fill this vacuum. It is the silent, invisible engine that powers the cosmos, a concept so strange and so beautiful that it continues to challenge and inspire physicists to this day. And as you drift deeper into relaxation, you can imagine this gentle, cosmic hum, the ever-present whisper of virtual particles dancing at the very edge of existence, a reminder that even in the most profound stillness, there is a universe of hidden life. The idea of virtual particles, these fleeting ghosts of reality, might still seem like a mathematical trick, a convenient fiction to make the equations work. But the universe has provided us with an even more direct and tangible proof of their existence, a phenomenon so strange, it sounds like it comes from science fiction. It is called the Casimir effect, and it is one of the most compelling pieces of evidence we have for the reality of the quantum vacuum. Imagine two large metal plates, perfectly smooth and uncharged. Now, imagine bringing them very, very close together in a perfect vacuum. We're talking about distances smaller than the width of a human hair, just a few micrometers apart. According to the classical physics of our everyday intuition, nothing should happen. They are uncharged, so there's no electrical attraction or repulsion. There's no air between them to push them around. They should just hang there, indifferent to each other's presence. But that's not what happens. In 1948, a Dutch physicist named Hendrik Casimir was working at Philips research labs. He wasn't actually thinking about the quantum vacuum at first. He was studying the forces between molecules, something called van der Waals forces. While wrestling with the complex calculations, a colleague, the famous physicist Niels Bohr, suggested something that seemed completely unrelated. He told Casimir to think about the problem in terms of quantum fields and the energy of the vacuum. Following this advice, Casimir made a remarkable prediction. He calculated that the two parallel plates would actually feel an attractive force, pulling them towards each other. This force, he proposed, came directly from the roiling sea of virtual particles in the quantum vacuum. The reasoning behind this is both subtle and profound. Remember that the vacuum is filled with virtual particles of all different wavelengths and energies. Out here, in the open space outside the plates, all possible wavelengths of these quantum fluctuations can exist. It's a chaotic, energetic party with guests of all sizes. But the space between the two plates is different. It's a much more confined environment. Because the plates are so close together, only virtual particles with very specific wavelengths can fit comfortably in the gap. The wavelength has to fit neatly between the plates, like a standing wave on a guitar string. Any fluctuation with a wavelength longer than the gap between the plates simply can't exist there. So, you have a situation where there are more types of virtual particles, more quantum fluctuations, pushing on the outside of the plates than there are on the inside. The space between the plates is a quieter, less energetic region of the vacuum. This imbalance creates a net pressure from the outside, pushing the plates together. It's as if the raucous party outside is creating more pressure than the small, quiet gathering between the plates. This tiny, subtle pressure difference is the Casimir force. Think of it like two ships floating side by side on a choppy sea. The waves in the open ocean can be large and powerful, pushing against the outer hulls of the ships. But in the narrow channel of water between the two ships, the larger waves are suppressed. The water is calmer. The greater pressure from the waves on the outside will gently push the two ships together. The Casimir effect is the quantum mechanical version of this phenomenon, with the virtual particles of the vacuum playing the role of the ocean waves. For years, this was just a theoretical prediction. The force Casimir predicted was incredibly small, almost immeasurably so. But as technology advanced, physicists were finally able to design experiments sensitive enough to detect it. In the late 1990s, experiments conducted by Stephen Lamoureux and later by Umar Mohideen and his team definitively measured the Casimir force, confirming Casimir's prediction with remarkable accuracy. They used a tiny sphere and a flat plate, measuring the faint attraction between them with a device called a torsion pendulum. The results matched the theory perfectly. This was a landmark achievement. It demonstrated, in a very real and mechanical way, that the quantum vacuum is not empty. It has real physical energy, and it can exert immeasurable force. The Casimir effect transformed the quantum vacuum from an abstract concept into a tangible part of our physical world. It proved that nothing can, in fact, push things around. The discovery has captured the imagination of scientists and science fiction writers alike. The idea of harnessing this vacuum energy is a tantalizing one. Could we build engines that are powered by the Casimir effect? Could we extract limitless energy from the vacuum itself? While the amount of energy we can currently access through the Casimir effect is minuscule, far too small for any practical application, it opens up a fascinating avenue of thought. It reminds us that the universe is full of hidden energies and unseen forces, and that our understanding of reality is always evolving. And so, as you continue to relax, you can visualize those two plates suspended in the quiet dark of a perfect vacuum. And you can imagine the unseen ocean of quantum fluctuations, the gentle but persistent pressure of virtual particles, pushing the plates together in a silent, cosmic embrace. It is a quiet testament to the power hidden in the void, a physical manifestation of the universe's restless heart. The Casimir effect gives us a tangible glimpse of the energy lurking in the quantum vacuum. But it begs a much larger question. Just how much energy is there in this emptiness? This leads us to one of the most profound and mind-boggling concepts in modern physics: zero-point energy. The term itself sounds like a contradiction. How can there be energy at point zero? But in the quantum world, zero is not what it seems. As we've explored, due to the Heisenberg uncertainty principle, a quantum system can never be perfectly still. A pendulum can't hang in a state of absolute rest. An electron can't sit motionless. There is always a minimum amount of residual jiggle, a fundamental vibration that can never be eliminated, no matter how much you cool a system down or remove all its energy. This lowest possible energy that a quantum system can possess is its zero-point energy. Every quantum field that fills the universe has a zero-point energy. The electromagnetic field has one, the electron field has one, and so on for all the other fundamental particles. The energy of the quantum vacuum, this supposed nothingness, is the sum of all these zero-point energies from all the different fields. It is the baseline energy of the universe itself. Now, here is where things get truly strange. When physicists try to calculate the theoretical amount of this zero-point energy, they arrive at a number that is frankly absurd. It's not just a big number. It is the most spectacularly, astronomically large number in the history of physics. The theoretical energy density of the vacuum is so immense that if it were real, its gravitational effects would be catastrophic. A cubic centimeter of empty space should, according to the theory, contain more energy than all the matter in the entire observable universe. It should have so much gravitational pull that it would have curled the universe up into a tiny ball smaller than an atom the instant it was born. Clearly, this is not what we observe. We live in a large, expanding universe, not a tiny, crushed speck. So, we have a colossal disagreement between what our best theory predicts and what our telescopes see. This is famously known as the cosmological constant problem, and it is arguably the biggest, most embarrassing unsolved problem in fundamental physics today. It represents a deep chasm in our understanding of how quantum mechanics and gravity fit together. So, what's going on? Why is the observed energy of the vacuum so much smaller than the theoretical prediction? Physicists have been scratching their heads over this for decades, and there are several competing ideas. One possibility is that our calculations are simply wrong. Perhaps we are misunderstanding something fundamental about how to sum up the zero-point energies of all the quantum fields. Maybe there's a hidden symmetry in nature, some unknown principle that causes most of these enormous energy contributions to cancel each other out almost perfectly. Imagine you have two gigantic numbers, but one is positive and one is negative. If they are almost exactly equal, they could cancel each other out, leaving only a tiny leftover amount. Some physicists speculate that a theory called supersymmetry might provide this cancellation mechanism. Supersymmetry proposes that every known particle has a superpartner with slightly different properties. The zero-point energy of a particle would be positive, while the energy of its superpartner would be negative, leading to a massive cancellation. The problem is, we haven't yet discovered any of these superpartner particles, despite extensive searches at particle accelerators like the Large Hadron Collider. Another idea is that the energy of the vacuum is indeed enormous, but it somehow doesn't produce gravity in the way that normal matter and energy do. Perhaps empty space, for some reason we don't yet understand, is gravitationally inert. This would be a radical departure from Einstein's theory of general relativity, which tells us that all forms of energy create gravity. A more exotic proposal is that the universe we inhabit is just one of countless universes in a vast multiverse. In this scenario, the value of the vacuum energy could be different in each universe. Most of these universes would have a huge vacuum energy, either positive or negative, and would either collapse instantly or fly apart so fast that stars and galaxies could never form. We, naturally, find ourselves living in one of the rare universes where the vacuum energy just happens to be small enough to allow for a stable, long-lived cosmos, and ultimately for us to be here to observe it. This is known as the anthropic principle. It's a controversial idea because it's very difficult to test, but it offers a potential, a somewhat unsatisfying explanation for our finely tuned universe. Despite this profound mystery, the concept of zero-point energy is not just a theoretical headache. It has real-world consequences, albeit subtle ones. For instance, it plays a role in the behavior of liquid helium. Even at absolute zero, the lowest possible temperature, liquid helium does not freeze solid under normal pressure. The zero-point energy of the helium atoms is great enough to keep them in a liquid state, a quantum jiggle that prevents them from locking into a crystal lattice. So as you rest, you can ponder this great cosmic mystery. You can imagine the immense, hidden energy contained within the space all around you, an energy so vast that its true nature eludes our greatest minds. It is a humble reminder that the more we learn about the universe, the more we realize how much we still have to discover. The quiet of the void is deceptive. It holds a secret energy, a zero-point hum that is both the foundation of our theories and the source of our deepest questions. The mystery of the vacuum's energy deepens when we turn our gaze from the incredibly small to the incredibly large, to the vast expanse of the cosmos itself. For decades, astronomers believed that the expansion of the universe, which began with the Big Bang, was slowing down. The gravitational pull of all the galaxies on each other should act like a brake, gradually reining in the initial outward rush. It was a simple and logical assumption. But in the late 1990s, two independent teams of astronomers made a discovery that turned cosmology on its head. By observing distant supernovae, which are exploding stars that serve as reliable standard candles for measuring cosmic distances, they found that the expansion of the universe is not slowing down at all. In fact, it's speeding up. Something is pushing the universe apart, acting like a kind of cosmic anti-gravity. This mysterious repulsive force was given a name, dark energy. We call it dark because we can't see it and we have no idea what it is. But whatever it is, it makes up about 70% of the total energy density of the universe. The matter that makes up stars, planets, and ourselves accounts for only about 5%. The rest is another mysterious substance called dark matter. So the universe is dominated by these two enigmatic components that we are only just beginning to understand. Now, where does the quantum vacuum fit into this cosmic picture? Well, the properties of this mysterious dark energy seem to be uncannily similar to the properties of the energy of the vacuum. Dark energy appears to be spread smoothly throughout space, and it has a constant density. As the universe expands, more space is created, and this new space comes with its own dark energy. This constant energy density provides a persistent outward push. This sounds exactly like the zero-point energy we were just discussing, a constant energy inherent to space itself. It led many physicists to a tantalizing hypothesis. Perhaps dark energy is the energy of the quantum vacuum. It's a beautiful and elegant idea, one that would connect the strange world of quantum mechanics with the grand scale of cosmology. It would mean that the accelerated expansion of our universe is being driven by the ceaseless fizz of virtual particles popping in and out of existence in the void. This idea actually has a long and interesting history. It goes back to Albert Einstein and his theory of general relativity. When Einstein first formulated his equations for gravity, he found that they predicted a universe that was either expanding or contracting. But at the time, in the early 20th century, the prevailing view was that the universe was static and eternal. To make his equations fit with this static model, Einstein reluctantly added an extra term, a sort of mathematical fudge factor, which he called the cosmological constant. He represented it with the Greek letter lambda. This cosmological constant acted as a kind of repulsive force, a property of space itself that would perfectly balance the attractive pull of gravity, holding the universe in a delicate, static equilibrium. A few years later, the astronomer Edwin Hubble discovered that the universe was, in fact, expanding. The galaxies were all rushing away from each other. Einstein immediately realized that his cosmological constant was unnecessary. He later called it his biggest blunder. He could have predicted the expansion of the universe years before it was discovered if he had just trusted his original equations. But the story doesn't end there. Fast forward to the 1990s and the discovery of the accelerating expansion. Suddenly, Einstein's blunder looked remarkably prescient. A cosmological constant, a repulsive energy inherent to space, was exactly what was needed to explain this cosmic acceleration. And so, the cosmological constant was resurrected. Now, here we are, with two seemingly related concepts. The cosmological constant, which we observe as dark energy, and the zero-point energy of the quantum vacuum, which is predicted by quantum field theory. It seems natural to equate the two. They both describe an energy that is an intrinsic property of space itself. But this brings us right back to the cosmological constant problem, the biggest puzzle in physics. When we measure the value of the cosmological constant, the strength of the dark energy driving the cosmic acceleration, we find that it is very, very small. It's a tiny, positive number. But when we calculate the theoretical value of the vacuum energy from quantum field theory, we get that astronomically huge number we talked about before. The discrepancy between the two is staggering. The observed value of the vacuum energy is about 10 to the power of 120 times smaller than the theoretical prediction. That's a 1 followed by 120 zeros. To give you a sense of scale, The number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. The mismatch is so colossal, so utterly mind-boggling, that it tells us we are missing something absolutely fundamental in our understanding of the universe. It's like trying to measure the height of a table, and your theory predicts it should be as tall as the entire galaxy, while your measurement shows it's only a few feet high. This discrepancy is a stark reminder of the deep divide that still exists between our two great pillars of modern physics: general relativity, the theory of the very large, and quantum mechanics, the theory of the very small. We need a unified theory, a theory of quantum gravity, to bridge this gap and explain how the quantum vacuum's energy actually behaves on a cosmic scale. So, as you float in the vastness of your imagination, you can picture the fabric of space-time itself, gently stretching and expanding. And you can visualize this expansion being driven by a faint, persistent energy, the whisper of the quantum void made manifest on a cosmic scale. The same quantum fizz that nudges an electron in a hydrogen atom is, it seems, pushing the galaxies apart. But the connection is shrouded in a profound mystery, a cosmic conundrum that hints at a deeper, more elegant truth about the nature of reality, still waiting to be discovered. The journey to our current understanding of the quantum vacuum is a long and winding one, built upon the shoulders of giants and punctuated by moments of brilliant insight and stubborn confusion. It is a story that begins not with the vacuum itself, but with the birth of quantum mechanics in the early 20th century, a revolution that shattered our classical deterministic view of the world. It all started in 1900 with a German physicist named Max Planck. He was trying to solve a problem related to the light and heat emitted by a hot object, known as black body radiation. The existing theories of the time failed miserably to explain the observed spectrum of light. In a move he himself described as an act of desperation, Planck proposed that energy was not continuous, but came in discrete packets, or quanta. The energy of light could only be emitted or absorbed in these tiny, specific amounts. It was a radical idea, the first suggestion that the world at its most fundamental level was not smooth, but grainy. This concept of quantization became the bedrock of the new quantum theory. A few years later, a young Albert Einstein took Planck's idea and ran with it, proposing that light itself was made of these quanta, which we now call photons. This explained the photoelectric effect, where light shining on a metal can knock electrons loose. Then, in the 1920s, a wave of brilliant physicists, including Werner Heisenberg, Erwin Schrödinger, and Niels Bohr, developed the full mathematical framework of quantum mechanics. It was during this period that Heisenberg formulated his famous uncertainty principle in 1927. As we've seen, this principle is the key to understanding why the vacuum can't be empty. By stating that there's a fundamental limit to how precisely we can know certain pairs of properties, like energy and time, it opened the door for energy fluctuations in the void. The next crucial piece of the puzzle came from a brilliant and famously taciturn English physicist named Paul Dirac. In 1928, Dirac formulated an equation that combined quantum mechanics with Einstein's special theory of relativity. The Dirac equation was a triumph. It described the behavior of the electron with incredible accuracy, and as a bonus, it predicted the existence of antimatter. But the equation also had a strange feature. It allowed for solutions with negative energy. A particle with negative energy was a bizarre concept. What would happen if an electron fell into one of these negative energy states? It would release an infinite amount of energy, which clearly doesn't happen. To solve this problem, Dirac came up with a bold and imaginative picture of the vacuum. In 1930, he proposed that what we perceive as empty space is not empty at all. Instead, it is completely filled with an infinite sea of electrons occupying all the negative energy states. This became known as the Dirac sea. According to Dirac, this sea of negative energy electrons is completely unobservable to us. It's the new definition of nothing. However, if you were to hit one of these negative energy electrons with enough energy, say from a powerful photon, you could knock it out of the sea and into a positive energy state. It would then become a regular, observable electron. But what about the hole it left behind in the sea? This hole, Dirac argued, would behave just like a particle with the same mass as an electron, but with a positive charge. The hole was the antiparticle of the electron. At first, Dirac thought this might be the proton, but it was soon realized that the particle had to have the exact same mass as the electron. In 1932, the American physicist Carl Anderson discovered this very particle in cosmic ray experiments and named it the positron. Dirac's strange idea about a filled vacuum had led to a stunningly accurate prediction. While the Dirac sea was a brilliant and useful concept, it had its own problems. The idea of an infinite sea of particles was a bit clunky, and it only worked for fermions, a class of particles that includes electrons, but not for bosons like photons. The modern understanding of the vacuum evolved with the development of quantum field theory in the mid-20th century, championed by physicists like Richard Feynman, Julian Shingyar, and Shinichiro Tominaga. Quantum field theory did away with the Dirac sea and replaced it with the picture we've been exploring tonight. In this view, the vacuum is not a sea of particles, but the lowest energy state of the underlying quantum fields. The particles are just excitations of these fields. The virtual particle-antiparticle pairs that pop in and out of existence are fluctuations of these fields around their ground state. This new picture was more elegant, more comprehensive, and it provided a more accurate and consistent way to calculate particle interactions. It's also important to remember the contributions of scientists who are often overlooked in the standard histories. For instance, the brilliant experimental physicist Chen-Xiang Wu, often called the First Lady of Physics, conducted a crucial experiment in 1956 that overthrew a long-held law of physics called the conservation of parity. Her experiment, which involved observing the decay of cobalt-60 atoms, showed that the universe is not perfectly symmetrical and can distinguish between left and right. This discovery had profound implications for our understanding of the weak nuclear force and the fundamental nature of particle interactions, which are all played out on the stage of the quantum vacuum. Her work was essential for establishing the standard model of particle physics, our current best description of the fundamental particles and forces. The history of the quantum vacuum is a testament to the power of human imagination and perseverance. It's a story of physicists wrestling with paradoxes, making bold predictions, and slowly, piece by piece, building a new and profoundly strange picture of reality. It began with the simple idea of a quantum of energy and evolved through filled seas of negative particles to our modern view of fluctuating fields. Each step along the way has brought us closer to the truth, while also revealing deeper and more fascinating mysteries. And as you drift off, you can appreciate the intellectual journey that has brought us to this point, a journey into the heart of nothingness, which has turned out to be the source of everything. The quantum vacuum is not just a curious feature of the universe. It is the very foundation upon which the stage of reality is built. In the framework of quantum field theory, the vacuum is the default state, the canvas on which everything else is painted. Every particle, every force, every interaction is, in a sense, a deviation from this ground state. The vacuum underlies all of physical reality. Let's think about a simple fundamental process. An atom emitting a photon of light. In our old, classical way of thinking, an electron in an atom is orbiting the nucleus. When it jumps to a lower energy orbit, it releases the excess energy as a photon. But why does it do this? What prompts it to jump? In a truly empty and static universe, an excited electron could, in principle, stay in its higher energy state forever. The answer lies in the quantum vacuum. The electron is not alone in its orbit. It is constantly interacting with the fluctuating electromagnetic field of the vacuum. It is being jostled by virtual photons that are constantly popping in and out of existence. These random vacuum fluctuations can tickle the electron, stimulating it to release its energy and fall to a lower state, emitting a real observable photon in the process. This is known as spontaneous emission. Without the ever-present hum of the quantum vacuum, excited atoms would never spontaneously emit light, stars wouldn't shine, and the universe would be a very dark and boring place. The vacuum's influence extends to all particle interactions. The standard model of particle physics, our most successful theory of the subatomic world, describes the fundamental forces of nature, electromagnetism, the weak nuclear force, and the strong nuclear force, as being mediated by the exchange of force-carrying particles. For example, the electromagnetic force between two electrons is described as the exchange of virtual photons between them. These virtual photons are not real observable particles. They are disturbances in the electromagnetic field, borrowed from the vacuum's energy budget, that carry momentum and energy from one electron to the other. Imagine two people on ice skates throwing a bowling ball back and forth. As one person throws the ball, they are pushed backward. When the other person catches it, they are also pushed backward. The exchange of the ball creates a repulsive force between them. This is a rough analogy for how the exchange of virtual particles creates forces. All the forces that govern our universe, with the exception of gravity, are mediated by these virtual particles, these fleeting messengers born from the vacuum. The vacuum, therefore, is not a passive backdrop, but an active participant in the fundamental workings of nature. Furthermore, the properties of the vacuum itself can be altered by the presence of matter and energy. This idea is central to our understanding of the strong nuclear force, the force that binds protons and neutrons together inside the atomic nucleus. This force is incredibly strong at short distances, but drops off very quickly with distance. The theory that describes the strong force is called quantum chromodynamics, or QCD. In QCD, the vacuum is a very complex place. It's filled with a seething condensate of virtual quarks and gluons, the force carriers of the strong force. This QCD vacuum has the strange property of confining quarks. You can never find a single quark on its own. They are always bound together in groups, like protons and neutrons. Trying to pull a quark out of a proton is like trying to stretch an elastic band. The more you pull, the stronger the force gets, until eventually the energy becomes so great that it's more favorable for the vacuum to create a new quark-antiquark pair from its own energy, snapping the elastic band and creating two new particles. This property of the vacuum is what gives protons and neutrons most of their mass. The mass of the individual quarks inside a proton only accounts for about 1% of its total mass. The other 99% comes from the kinetic energy of the quarks and the energy of the gluon field that binds them together, a direct consequence of the complex structure of the QCD vacuum. This leads to a profound realization: the very substance of the world around us, the mass of the matter that makes us up, is largely a consequence of the energetic and complex nature of the vacuum. The ultimate goal of fundamental physics is to create a single, unified theory that can describe all the forces of nature, including gravity. This hypothetical theory is often called a theory of everything. Many physicists believe that a true understanding of the quantum vacuum will be a crucial component of any such theory. The vacuum is the point of intersection between quantum mechanics and general relativity. It is where the energy of quantum fields meets the curvature of spacetime. The cosmological constant problem is the most glaring symptom of our failure to reconcile these two theories. A successful theory of quantum gravity must be able to explain why the vacuum has the specific energy value that it does. So, the vacuum is not just empty space. It is the source of spontaneous emission, a medium for all fundamental forces, the reason for the confinement of quarks, and the origin of most of the mass in the universe. It is the central player in the drama of particle physics, and the biggest stumbling block on the road to a unified theory. As you continue to rest, you can imagine this intricate and active void, not as an emptiness, but as a rich and complex medium, the fundamental substance from which all the laws and particles of our universe emerge. It is the silent, beating heart of reality itself. The bizarre and counterintuitive nature of the quantum vacuum, while still deeply mysterious, opens up a realm of tantalizing possibilities and potential implications that stretch from practical technologies to the very origin of the universe. While some of these ideas remain firmly in the realm of science fiction for now, they are rooted in the solid ground of theoretical physics and inspire us to ask, what if? One of the most captivating prospects is the idea of harnessing the vacuum's energy. We've seen how the Casimir effect demonstrates that this energy can produce a real mechanical force. This has naturally led to speculation about vacuum energy engines or zero-point energy collectors. The allure is obvious. If the vacuum contains an enormous amount of energy, as theory suggests, then tapping even a tiny fraction of it could solve all of our energy needs forever. It would be a source of clean, limitless energy, available everywhere in the universe. However, the reality is far more challenging. While the Casimir force is real, it is incredibly weak and only acts over microscopic distances. Extracting useful work from it is a monumental engineering problem. Think of it like trying to power a city with the gentle breeze from a butterfly's wings. While there is energy there, capturing it efficiently on a large scale is beyond our current capabilities. Furthermore, many physicists believe that, due to the laws of thermodynamics, you can't get free energy out of the vacuum. Just as you can't power a boat by scooping up the calm water of a lake and pouring it back in, you likely can't extract net energy from the vacuum's ground state. You might be able to create interesting effects with it, like reducing friction in tiny micro-machines, but a perpetual motion machine powered by the void is probably not on the cards. But the vacuum's influence extends to far more exotic phenomena, particularly around one of the most extreme objects in the universe, a black hole. In the 1970s, the brilliant physicist Stephen Hawking made a stunning theoretical discovery. He showed that black holes are not completely black. They should, in fact, glow faintly, emitting a steady stream of particles. This phenomenon is now known as Hawking radiation. Hawking's insight was to combine quantum field theory with the intense gravity around a black hole. He considered what happens to the virtual particle-antiparticle pairs that are constantly popping into existence in the vacuum, near a black hole's event horizon, the point of no return. Usually, these pairs annihilate each other almost instantly. But near an event horizon, it's possible for one member of the pair to fall into the black hole while the other escapes. Imagine a pair of virtual particles, an electron and a positron, appearing right at the edge of the event horizon. The positron might be captured by the black hole's immense gravity, while the electron has just enough energy to fly away into space. To an observer far away, it would look as if the black hole has just emitted an electron. Because the escaping particle has positive energy, the particle that fell into the black hole must have had negative energy in order to conserve the total energy. By swallowing a negative energy particle, the black hole actually loses mass. Over immense periods of time, this slow leakage of Hawking radiation will cause the black hole to evaporate and eventually disappear completely. This process is a beautiful synthesis of quantum mechanics, general relativity, and thermodynamics, and it all hinges on the existence of vacuum fluctuations. It tells us that even the most formidable objects in the cosmos are subject to the subtle fizz of the quantum void. The vacuum is not just a stage for events. It actively participates in the life and death of black holes. Perhaps the most profound implication of the quantum vacuum relates to the origin of the universe itself. The Big Bang theory describes how the universe evolved from an incredibly hot, dense state, but it doesn't explain what caused the Big Bang in the first place. What came before it? Where did all the matter and energy in the universe come from? One speculative but compelling idea, proposed by physicists like Alan Guth and Andre Linde, is the theory of cosmic inflation. This theory suggests that in the very first fraction of a second of its existence, the universe underwent a period of mind-bogglingly rapid exponential expansion. It grew from a size smaller than a proton to something roughly the size of a grapefruit in an infinitesimal amount of time. This inflationary period would have been driven by the energy of a quantum field trapped in a false vacuum state, a state with a very high energy density. This false vacuum energy would have acted like a super-powerful form of dark energy, causing space-time to expand at an explosive rate. Eventually, this false vacuum decayed into the lower energy true vacuum that we inhabit today, releasing its stored energy in a massive flood of particles and radiation. This event, the end of inflation, would have been the bang of the Big Bang, setting the stage for the universe as we know it. In this picture, the entire universe, with all its galaxies, stars, and planets, is ultimately the product of a quantum fluctuation in the vacuum. It's an idea sometimes summarized as the ultimate free lunch. The universe could have arisen from essentially nothing, a random quantum burp in the primordial void. This idea even opens the door to the possibility of a multiverse. If our universe was born from a quantum fluctuation, perhaps other, similar fluctuations could happen elsewhere, spawning other universes with potentially different physical laws. So, from the subtle nudge that causes an atom to shine, to the slow evaporation of black holes, to the very origin of our cosmos, the quantum vacuum plays a central and creative role. It is not just the foundation of reality. It may well be the source of it. As you settle into a state of deep rest, you can let your mind drift on these incredible possibilities. You can imagine the silent, creative power of the void, a cosmic womb from which entire universes might be born. It's a humbling and awe-inspiring thought, a reminder that the greatest secrets of existence may be hidden in the quietest and most overlooked corners of the universe. For all that we have learned about the quantum vacuum, it remains one of the most enigmatic and challenging frontiers in science. Our theories have given us a tantalizing glimpse into its nature, but they have also thrown up profound paradoxes and left a trail of deep, unanswered questions. The void is where our best theories collide, and it's in the heart of this collision that the greatest mysteries lie. At the very top of the list, as we've discussed, is the cosmological constant problem. It cannot be overstated how significant this problem is. The discrepancy of 120 orders of magnitude between the theoretical prediction for the vacuum's energy and the value we observe through cosmic expansion is the largest disagreement between theory and experiment in all of science. It is a gaping wound in the heart of modern physics. It tells us in no uncertain terms that our understanding of how quantum energy gravitates is fundamentally, catastrophically wrong. Solving this problem is the holy grail for many theoretical physicists. Is the answer a new symmetry of nature, like the proposed but undiscovered supersymmetry? Does it require a radical rethinking of Einstein's theory of gravity? Or is the answer hidden in the strange logic of the anthropic principle and the multiverse? We simply don't know. Finding the solution will almost certainly require a full-blown revolution in our understanding of physics, a new theory of quantum gravity that can seamlessly unite the worlds of the very large and the very small. Another major challenge is the difficulty of studying the vacuum directly. The fluctuations of the vacuum are, by their very nature, incredibly fleeting and occur on the smallest possible scales. We can't build a microscope powerful enough to see virtual particles popping in and out of existence. Our evidence for them is indirect, though compelling. We see their effects in the Lamb shift, in the anomalous magnetic moment of the electron, and in the Casimir effect. These phenomena are like the footprints of an invisible creature. We can see where it has been and how it has disturbed its surroundings, but we can't see the creature itself. Physicists are constantly devising new and more clever experiments to try and probe the vacuum's properties. Some experiments look for tiny temperature-dependent shifts in the Casimir force. Others are trying to observe a phenomenon called the dynamical Casimir effect, where a rapidly moving mirror in a vacuum is predicted to convert virtual photons into real, detectable photons. It's like shaking the quantum vacuum so violently that some of its energy spills out as light. These experiments are at the cutting edge of technology and push the limits of what is possible to measure. Then there is the question of the vacuum's stability. Our current vacuum, the ground state of all the quantum fields, appears to be stable. But is it truly the lowest possible energy state? Some theories, including the standard model of particle physics, suggest that our vacuum might be a false vacuum. As we explored in the context of inflation, a false vacuum is a state that is stable for a while, but not eternally so. It's like a ball resting in a small dip on the side of a large hill. It's stable for now, but a big enough nudge could send it rolling down to the much lower valley below. If our universe is in a false vacuum state, it's possible that at some point in the distant future, a quantum fluctuation could trigger a transition to the true vacuum state. A bubble of this new true vacuum would appear somewhere in the universe and expand at the speed of light, converting the old vacuum into the new one as it went. The laws of physics inside this bubble would be completely different. The fundamental constants could change, and the very structure of matter as we know it might not be possible. While this vacuum decay event is a theoretical possibility, calculations suggest that the lifetime of our current vacuum is extraordinarily long, many, many times the current age of the universe. So, it's not something to lose sleep over. But it's a fascinating and humbling thought that the very ground of our being might only be metastable. Finally, the quantum vacuum is central to the quest for a unified theory of everything. How does the vacuum behave in the extreme conditions of the Big Bang or inside a black hole? How does it relate to the nature of space-time itself? Is space-time a fundamental entity, or does it emerge from a more fundamental, underlying quantum reality, perhaps related to the vacuum? These are the kinds of questions that drive the fields of string theory and loop quantum gravity, two of the leading approaches to developing a theory of quantum gravity. These challenges and mysteries are not signs of failure. They are the signposts of discovery. They mark the edges of our knowledge and point the way toward a deeper understanding of the cosmos. The quantum vacuum, once thought to be the definition of nothing, has turned out to be a place of immense complexity, profound creativity, and deep mystery. It is a reminder that the universe is far stranger and more wonderful than we can possibly imagine. And so, as you lie here on the cusp of sleep, you can let these great cosmic questions wash over you. You can embrace the not knowing, the profound and beautiful mystery that lies at the heart of reality. You can find a sense of peace in the knowledge that we are part of a universe that is still unfolding, still revealing its secrets. The quiet hum of the quantum vacuum is a lullaby of infinite possibility, a gentle reminder that even in the deepest stillness, the universe is alive with a silent, creative energy, a power that fuels the stars, expands the cosmos, and perhaps even dreams of itself through us.